there, welcome back to Life Lessons from Math. As always, I'm your host Wesley, and I just wanted to start off by apologizing for, taking a couple of weeks to get videos uploaded again. But the past couple of weeks were finals week, or the week before finals week at my school, and so, that's just kind of a busy time of the year. But now that I'm on summer vacation, I'm hoping to be able to start uploading videos regularly again. And something I wanted to run past you guys is an idea that I had. So what I'm wanting to do is basically start uploading 2 videos a week. Probably one on Monday, one at the beginning of the week, and one at the end of the week. Probably Monday, Friday type thing. And basically once I finish the Intro to Calculus series, what I'm wanting to do is have like one video of the week be kind of what you've seen so far, like the big picture ideas, what is a limit, a little bit of how it works, and then a second video where I do a deep dive and really dig into the nitty gritty, the gory details, and basically put some, more advanced mathematics up here, but explain to you guys what I see when I see the math of like, okay, that looks like a crazy bunch of symbols, Wesley. What's that mean? And why do you use Greek so much? Good questions. But yeah, let me know if you would like to see that down in the percentage section. And I will, again, that's just something I was thinking about doing. So, sweet, with that being said, let's jump into the video. So, remember, just as a super brief refresher since it's been a minute, in the last video where I talked about limits, I basically introduced this thing, which I called the limit, which is the fundamental building block of analysis, because it allows us to understand what happens to functions and quantities whenever it approaches some problem area. What happens when we approach something like 0 divided by 0, or infinity divided by infinity, that kind of stuff. Like, limits are the tool we use to understand such weird phenomena. And because they're so useful in that way, we'll need them to basically be able to understand the rest of calculus. Because calculus and most of mathematics is about trying to overcome difficulties and challenges that we face. And so the limit is a really powerful tool for helping us to overcome those difficulties and challenges. So, with that kind of brief recap, the motivating question for today's video is, what is the slope of a tangent line? If you don't remember what a tangent line is, that's okay. I'll get into that in just a second. But I did just want to point out that this question is one of the 2 questions that prompted the discovery of calculus. Calculus was discovered by Isaac Newton and Gottfried Leibniz a few hundred years ago, and there were 2 questions that prompted it. One of them is what is the slope of a tangent line? We'll talk about the second question in the next video when we talk about integrals. So, with that being said, what is the slope of a tangent line? Well, what is a tangent line? Basically, to understand what a tangent line is, I want to start by introducing, what is a secant line? A secant line is a line that is determined, not necessarily that goes through 2 points, but that is determined by 2 points on a graph. So if we have some function, y equals f of x, and we look at its graph, and I pick 2 points on it, the secant line is the line that goes between the 2 points. Again, technically, if I were to change this graph a little bit, it might go through a 3rd point. Eventually this would cross through there, but it's only determined by 2 points. And so that's a secant line, and we know how to find the slope of a secant line relatively easily, right? As long as we have 2 points, we have a handy-dandy formula. And just to kind of refresh that formula, remember slope is rise over run. And in particular, when we know what the function is, we can write a formula for rise over run down. Remember, the slope is usually denoted by m, and we would write the rise as f of x2 minus f of x1 all over x2 minus x1. And so this is the formula for the slope of any secant line. Again, just following the standard rise over run formula. the problem with a tangent line, and why this is, this was a challenging problem to answer, is, well, what if we only want to use one point to determine the line? And in particular, we want to do more than just use one point to determine it. We only want it to touch the graph at one point. It's like, I only want it to touch there. Again, if I were to kind of curve this down, it can cross in other places, but at least nearby it, it only touches there, barely touches it. Does that make sense? And so that's a tangent line. And well, we can't use this formula anymore because this requires 2 x values to be able to use. And here we only have 1 point. So how do we find the slope of this thing? Well, that's what a derivative is useful for. Okay, so that's just the motivating question. That's the thing we're looking for. And I'll explain a little bit of why we want to understand the slope of tangent lines in just a second. Okay, so what is a derivative? Well, essentially a derivative is a tool we use to answer this question. A derivative is something that allows us to find the slope of a tangent line. Easy enough, but what does it do? Why do we care about the slope of tangent lines? Well, fundamentally, there are a few different reasons. Derivatives are incredibly useful, and they have wide applications, but I'm going to kind of focus on 2 in today's video, and I'll kind of highlight a third one, though I won't go into super great detail on it. So, one reason that derivatives and finding the slopes of tangent lines are incredibly useful is they allow us to linearize a function. So basically, notice in this picture, especially like as I'm close to the point where my tangent line touches, it's almost indistinguishable. You can't distinguish the function from the tangent line. The function and the tangent line look basically the same here. And so that allows us to replace some complicated function with just a line, right? Linear stuff, i.e. stuff that deals with lines, are the most straightforward things within mathematics, which is why, we use that kind of terminology even colloquially of like, oh, that was linear, that was straightforward, And so there's a whole branch of mathematics dedicated to understanding how the linear stuff works, how the line stuff works, but again, that's one fundamental reason derivatives and tangent lines are so useful. And this is useful even in research level mathematics. I use this idea all the time, and I think in basically every research paper I've done, I've used this idea. So this is a really powerful tool, and I'll break it down a little bit more later on in the video, but just to hint a little bit at the life lesson behind this, what are we doing? We're taking something complicated and replacing it with something simple, and then by studying something simple, we're able to slowly work our way back up to the complicated. And so, again, a little bit of a foretaste of the life lesson there. And then, not only that, derivatives allow us to understand when a function is increasing, i.e. when things are looking up, and when a function is decreasing, i.e. when things are kind of looking down. And those kind of have natural implications, I think, for our lives. But more than that, mathematically at least, whenever we're able to determine when a function is looking up and looking down, well, where those two things meet, where you have something that's up to down, you have a peak, right? You kind of have a mountaintop experience, and mathematically that's called a maximum. And so if you wanted to maximize profits, derivatives would be a good way to do that because, again, using the slopes of the tangent lines, we can figure out where this maximum occurs by just looking at the slopes, if that makes sense. And then same thing, if you want to like minimize cost of a function, you can look at, well, where does it go from decreasing to increasing? Where do the valleys happen? Does that make sense? And, that is really useful for optimizing problems. It's useful for graphing functions. There's a lot of uses for understanding increasing, decreasing natures of a problem. And kind of the third thing that I won't necessarily spend a ton of time on today is that derivatives fundamentally tell us how things change, right? That's what a slope really is. A slope really fundamentally tells you how things are changing. Whenever you're looking at the slope of a secant line, it tells you how things are changing over an average time interval. It's like, okay, my average speed from point A to point B was 50 miles per hour. That is the average rate of change. But at any given moment, you can look at your speedometer, which basically behaves like a derivative, and be like, okay, at this moment, I'm going 60 miles per hour. And so a derivative allows you to understand how things are changing in a moment, at a point in space or a point in time. Does that make sense? And so that ability to understand how things change is really useful both mathematically and for our lives. You know, something I find very helpful in my own life is just understanding how I change over time. Like, when am I in a season of growth? When am I in a season of decline? That kind of stuff. And so, again, just kind of hinting a little bit at the life lessons as, you know, at the beginning of the video. So, with that being said, a derivative allows us to do all that fun stuff. So, how? How does it work? How does it relate to the slope of a tangent line? How does it do those different things? Well, let's dive in, shall we? Basically, the idea behind answering the question, what is the slope of a tangent line, is to look at the slope of secant lines and then to use a limit to understand what happens as those secant lines get closer and closer to a tangent line. So let's get a picture going to be able to understand this. So we're looking at our function y equals f of x. And again, we're just going to pick our favorite number, and we're going to call that number a. So we have our favorite number a here, and we want to find the slope of that tangent line, you know, where it just barely touches there. This is our goal. Well, like I said, we don't, at the moment, know how to answer that question, so what we're going to do is to use secant lines. So let's say we have an x value way over here, and it's like, okay, well, when I have a point x and a point a, I can find the slope of that secant line. And so what is the slope of that secant line? Like I said earlier, it's the change in the y values minus the change in the x values. All right, so that's the slope of our secant line. But looking at this picture, it's like, well, that secant line's not that close to our goal. It's pretty far away from it. So what happens if we move x closer? It's a little cattywampus. There we go. If we move x closer, we'll notice all of a sudden this line is a lot closer to our goal than this line. And so what we want to do is keep moving x closer and closer to a. And what we'll find is that as we move x closer and closer to a, is we arrive at our goal. And so we have to do that from both the right and the left. And so when we do that from the right and the left, we arrive at our goal, our tangent line. Does that make sense? And so just kind of using this picture as motivation of like, hey, I want to use what I know, I want to use the secant lines that I understand to approximate the tangent line that I don't understand. And so we take the limit as our x values approach our favorite number. Oh, I meant to draw an arrow here, right? Because they're approaching it from the right, approaching it from the left, and that gives us what we're going to call the slope of the tangent line. And not only does it give us the slope of the tangent line, this is what we're going to call the derivative of f at a. And so the derivative of f at a is given by this limit definition. And And again, that limit definition tells us the slope of a tangent line. And I just kind of want to point out, we really do need a limit here to understand this, because what happens at A? If we replace x with A, what would we get? We would get f of A minus f of A all over A minus A. Well, f of A minus f of A, that's 0. A minus A, that's 0. 0 over 0. How do we understand that stuff? Well, we use limits. And so we really do need a limit to be able to define the slope of a tangent line. And then we're going to define that slope of a tangent line as a derivative. And so we have a few different notations for the derivative, and I'll break those down in future videos, but for now I'm just going to kind of stick with one notation. So if we have our original function as y equals f of x, then my derivative is going to be a new function. So using this limit definition, I can define a new function that I'm going to label y equals f prime of x. And so just to provide a little bit of motivation for why we call this a derivative, what is a derivative colloquially? Well, a derivative colloquially is an object that comes from another object. You know, like wood is a tree derivative. It's a derivative from trees because wood comes from trees. Or, yeah. And wool socks is a derivative of wool because wool comes from socks. And so a derivative is a function that comes from some original function, and this derivative tells us the slope of a tangent line at any point x. And so basically, I can extend this definition a little bit to give me any point, not just my favorite number, but I can replace my favorite number with any number and get this function out that tells me the slope of the original function at that point x. Does that make sense? And so we use the notation f prime because the f is there to say, like, hey, my original was f, but the prime says I'm different. I came from f, but I'm different. And in particular, the prime tells me that I took the derivative, i.e. I found the slope of the tangent line, or the rate of change, as I kind of mentioned earlier. Does that make sense? So with that being said, this is how we answer this question. This is how a derivative is defined, but I want to take a little bit of a moment to talk about this limit definition. So the limit definition is not really practical in Calculus 1 types courses. You know, students usually have to practice this limit definition, and I'll motivate why they practice it in just a second. But one, it provides the intuition as to why the derivative actually tells you the slope of the tangent line. This definition, even though it's a little unwieldy because of limits, is extremely useful because it's where it comes from. And when you understand where something comes from, you can understand what something does. But, you know, it's, like I said, it's a little unwieldy to take limits every time we want to find a derivative. And so basically what people have discovered over the years is just by using this over and over again, they discovered that derivatives obey certain rules. They have guidelines that they have to follow. And, you know, people, as they discovered these rules, wrote them down, and now today we can benefit from that just by using those rules to find derivatives rather than having to use the limit definition. So, just to give, I actually want to keep the limit definition up for now, but I'll erase this other stuff. But to give some examples of that, you know, if we have something like f of x is equal to, I don't know, x squared, I can use what's known as the power rule to tell me that the derivative is just 2x. So rather than having to go through this limit stuff every time, the power rule just says, hey, you bring the power down and you subtract 1. So I bring the 2 down, I subtract 1, so 2 minus 1 is 1. And so, does that make sense? And there are rules to handle just about every conceivable type of situation, whether it's a power, an exponential function, a logarithmic function, a trigonometric function, two functions multiplied together, two functions divided by each other, a function inside of a function. There's rules to handle basically every conceivable situation to help us actually practically calculate derivatives rather than use this limit definition. But this limit definition is extremely useful, not just for providing motivation and seeing where derivatives come from, but it also is useful in research level mathematics, because in research level mathematics we don't have those rules yet, because we're not dealing with real valued functions, right? This is what's known as a real valued function because I put in a number and it gives me a real number out. And when you're dealing with, like, let's say a matrix valued function, i.e. you put something in and it spits out a matrix, or, you know, there are other mathematical objects that are a little bit challenging to describe, but when you're dealing with those things that give you these weird objects out, we don't have rules to follow. We have to use this limit definition to actually find derivatives. And so, you know, it is important, even if we practically have rules that we can follow to help us find derivatives. And so, with that being said, I want to start heading into kind of the application. So remember, the first thing I said is that derivatives help us find linear approximations. So just to kind of refresh your memory on that, let's say I'm looking at some function y equals f of x, and I want to find the tangent line to that function. Like I said earlier, as long as you're sufficiently close to your favorite number, a, right? As long as you're sufficiently close to a, the line and the function are basically indistinguishable from one another. And so that leads to the idea that we can say that my function is approximately equal to my tangent line as long as x is near my favorite number a. And so this idea, like I said, is incredibly important, but before I kind of get too much into it, let's actually figure out what this formula is. Remember, the formula for a line, like a tangent line, is y minus y1 is equal to m times x minus x1. This is the point slope form. You might also remember the slope-intercept form, y equals mx plus b. They give you the same answer. This is just a little bit more convenient for the purpose that I want to give in today's video. So basically you need to know a y value, an x value, and a slope, and then you can find the equation of a line. And so here we know our x value, right? So we know our x value is a. Remember, the slope of the tangent line is the derivative, so my slope is f prime of a. And so we just need to find the y value, and the y value just comes from plugging a into f of x, right? Y equals f of x, so this is just f of a. And so boom, we have an equation for our tangent line. And so all we have to do is add f of a over, and we have it in terms of y explicitly. So y is f of a plus f prime of a times x minus a. And so this tangent line is going to be roughly equal to my original function as long as x is near a. So a practical example of this is we can replace sine of x with x as long as x is near 0. And so that's pretty handy, right? As long as I'm close to 0, I don't actually have to use the trig function sine. I can just use the function x. And that's really nice, because most people don't like trig, and so it's like, rather than deal with something really complicated like sine, I can just deal with the function y equals x and be like, that's a lot easier to deal with, right? So does that make sense, this idea of approximating the complicated function with the linear function, the line? Basically because by picture, the two are indistinguishable from one another. They look basically the same. And so, why is this useful mathematically? Well, basically, what I want to kind of point out is that we can write f of x as the linear part, right, this thing, and then plus the nonlinear part, basically everything else. It's like, okay, we have the nice linear part that comes from my derivative, my tangent line, and then the nonlinear stuff, which is literally everything else. And so mathematically what we often do is we look at the linear part, we study how stuff behaves if everything were just nice and perfect and linear the way we want it to be. And then we add in the complexities, we add in the nonlinear stuff, and we basically try to show that the linear stuff allows us to control the nonlinear stuff. Once we understand this problem, we understand the whole thing is the goal. You know, sometimes that works, sometimes that doesn't. It depends on the structure of the function involved, but that's the idea. And so, you know, how does this work practically? How does this work in life? Well, you know, often when you're learning something, you have to start off with the linear stuff, the stuff that's straightforward, and then you can add in the complexities, the nonlinear stuff, right? So like these YouTube videos, for instance, they're raw, they're unedited, because when I'm starting this channel out, I'm not wanting to like become a YouTube expert overnight. It's something I'm learning as I go, and right now I haven't really taken the time, because I was in grad school, to learn how to edit videos. And so for me, that's the complex stuff, the nonlinear stuff. Right now, I'm just focusing on recording them, and then I'll work my way to this. Does that make sense? And so, I don't know. I hope that gives a little bit of insight into, you know, how we learn just in general. People in general have to start usually with the simple, and then you add in all the layers and complexity to it. So, cool. So this is one of the most powerful research tools in all of mathematics, and I hope I made it clear how that works. But kind of the second thing I wanted to talk about, and I'll try to go through it quickly because I think this video is getting a little long, is basically how a derivative allows us to study when a function is increasing, decreasing, and all that stuff. So basically, when a derivative is positive, that tells me that my original function is increasing. So why is this true? Well, remember, the derivative tells us the slope. It tells us how things are changing. So when the slope of a line is positive, remember, a positive line slope looks like this. As you go to the right, it goes up. And so mathematically, we call that an increasing function. And so, you know, just by looking at the sign of the derivative, we can tell if it's increasing. Well, what happens if the derivative is negative? Well, that tells me that my slope is negative, i.e. things are kind of looking down. And so my original function is decreasing. And, you know, I want to stop and talk a little bit about the life lesson here. You know, what in your life is a positive derivative? What in your life tells you that things are looking up? What tells you that you're in a season of growth, that you're growing, that you're in a healthy place? So for me, one of my positive derivatives, the indicators that I'm growing is when I'm reaching out to my friends consistently and trying to engage with them, just because I can struggle sometimes with social anxiety or, you know, just fears and insecurities. And whenever I'm actively reaching out to people, that tells me that I'm pushing past those fears, I'm pushing past those insecurities, and I'm trying to grow as a person. Does that make sense? And conversely, when the derivative is negative, what in your life is like a negative derivative? What in your life tells you that you're in a state of decline, that you're heading towards an unhealthy place, that, you know, things are kind of looking down? So again, for me, apathy. When I get apathetic about stuff, when I don't want to take care of myself, when I don't want to sleep, when I nothing sounds appealing to me at all, that's an indicator that I'm heading towards an unhealthy place, you know. It's a pretty strong indicator that I'm heading towards an unhealthy place. And when you can recognize these things in your life, these things that tell you that you're growing or these things that tell you that you're declining, they allow you to basically push towards a place of growth, right? We want to develop as people, and to really be able to do that, we need to be able to recognize, well, when am I in an unhealthy place? Because when you can recognize you're in an unhealthy place, you can reach out, you can try to get help, you can try to choose things differently. It's a lot easier said than done. You know, I'm not asking you to pull yourself up by the bootstraps. You know, I'm not saying, belly up to the bar and just get happy, right? No. No. It's hard, you know. Life is not just something that you do. It's not just something you just choose to be healthy and happy. But when you recognize the signs in your life, the red flags that say, I'm heading towards an unhealthy place, you can, again, it makes it easier to recognize that and try to live differently and strive for health, strive for growth. Does that make sense? You know, it's not something you just immediately turn up. And so just as a picture, what it might look like is it's like, okay, I'm heading up, and then something happens, some critical moment in our life happens that kind of starts us heading downhill again. We're heading towards an unhealthy place. But when I recognize that I'm heading in an unhealthy place, I might be able to, you know, reach another critical moment. It's like, okay, I've recognized that I'm heading in an unhealthy place, and then I could either try to change, or I can basically do nothing and just keep being unhealthy. And so when I reach this critical moment, I have kind of a choice to strive to do better. And notice you don't immediately get back up to where you were. You know, it takes time to grow back to where you were again. Does that make sense? I hope it does, and I hope it's encouraging, you know, to just think about, well, when am I increasing? When am I decreasing? And these critical moments in our life are actually related to, well, what happens when the derivative is 0? Because here, if you notice, kind of the tangent line is horizontal. And so, well, the tangent line is horizontal when the slope of the tangent line is 0, and so when f prime of x is 0, that implies, you know, usually some kind of constant moment, you know, where we kind of have this decision, something that forces us to change, usually. And then, I hope this is all making sense. And the last option for derivatives is that the derivative straight up does not exist. So mathematically, when we see d and e, that just means does not exist. And what this would mean for a function is that there's some kind of abrupt change, some sharp change in the graph. And derivatives don't like abrupt change. They don't like sharp change. And it's like, I can kind of relate to that. Most people don't like abrupt or sharp change. We are like a derivative in a lot of ways. We don't do well with it. You know, or it could mean there's some kind of blow up. You know, basically something goes to infinity. Something just gets exponentially harder and we can't deal with it, and so we call that mathematically a blow up. And so some of these abrupt changes that derivatives don't like are, you know, corners. It's like, I was heading in this direction in what I thought was a pretty straightforward manner, and then all of a sudden, like, boom, I'm heading in a completely different direction. It's just kind of sudden. Or a cusp. So a cusp would look something like this, where it's like I was heading up in this direction, and then all of a sudden I'm very sharply heading down. And so these two are known as critical points, where there's a sharp or sudden change in a direction. And so these critical points mathematically, or these critical moments in our lives, are really important because they sort of change the trajectory of our lives, whether we're growing or whether we're declining, and being able to recognize those and seek help and manufacture our own critical points is really helpful. So, with that being said, the last thing I want to say is notice that these are the maximum and minimums of the function. It's like that's the biggest point on the graph or the lowest point on the graph. And so mathematically, why are critical points important? Well, that's how we optimize functions. It's like, oh, that's how we find the maximum profit or minimize the cost, is looking at these critical points mathematically. So that's the introduction to derivatives that I want to give. I hope, again, I know I've said this a lot, but I hope I've made it clear and enjoyable, and that the life lessons were good and rich for you. And so again, if you have questions, leave them down in the percentage section. If you're interested in the deep dive videos, leave your thoughts on that down below as well. And with that being said, I hope you guys are doing well and have a great day. Bye.